So in this video, we are going to talk about weighted properties method in material selection. And our focus will be on the digital logic approach. In most applications, the selected material should satisfy more than one functional requirement. So in this method, each material required is assigned to a certain weight. Okay, and on this weight, we are able to calculate its performance index. So we have our basic formula in which that the performance index is equal to the summation of I is equal to 1n beta I times wi. I'm going to explain this variables. When we take this gamma represents the performance index. And then when you calculate for the performance index for a material, or when given several materials, and the material which has the highest performance index, that means that material will be the suitable material for the application. Now the beta I is called the scaling factor. And note that the scaling factor is always less than or equal to 1 as when you're working in fraction or in percentage, 100%. So let's note that. And our WI is called the weighting factor or index. And that one too has a condition that should be less than or equal to what? 1. So we have several methods of finding the weighting factor. That is the main purpose, right? So with the weighting factor, you need to find the weighting factor. Well, they'll give you a sample question. We're going to solve a sample question in this video for us to understand how we can use the digital logic approach and also how we can find the scaling factor and the weighting factor, right? So one thing that you should know about that is that with the scaling factor, right, we have the weighting factor WI, or the scaling the weighting index. Sometimes they will give you the weighting index, so you don't need to find the weighting index. But with the digital logic approach, right, what to say that when many materials properties are used to specify the performance, it may be very difficult, okay, to establish the weighting factors. So in this case, one way of doing this is that we use the digital logic approach, and that makes it very easier for that. And with a digital logic approach, is a logic approach. So my way of doing it might be different from yours, but at the end we should all get the same material selection, okay, or material selected. So let's look at this. How do we do it? So the step is that each property is listed and is compared in every combination. So we talk about combination. So combination. So before you can solve this, right, what you need to know is that you need to know the combination. So the combination, how do you find the combination? Now the combination formula is equal to the capital N is equal to small n, bracket open, n minus 1 divided by 2, whereby this capital N represents the combination and the small n represents the number of properties given to you. So the number of properties given to you. So if the number of properties that you've solved or given to you in the question is like 5, you're going to get that the combination is going to give you n is equal to what? 5 brackets open 5 minus 1 divided by 2, which will give you 10 combinations. So you know you have 10 combinations, right? You're going to solve a practical example and you know how to do it. So finding the 10 combination, then you go on with your digital logic approach table and then you find it. Now, the digital logic table will help you to what? Have a positive decision, and through the positive decision, you're going to get your weighting index or weighting factor. So what you need to do, the property that is considered to be more important of the two is given 1, and the one which is not important is given what? 0. So you are going to take 2 at a time. So if they have toughness and strength, so toughness and strength, when you are comparing them, which one is more important? Maybe toughness. So toughness is 1 and strength is 0. So for us to understand it better, let's take an example that we have done here. So in this example, let's read the question together. They say what? The material selection for a cryogenic storage vessel for a liquefied propane gas is being evaluated on the basis. So we have the toughness, we have the elastic modulus, we have the specific gravity, we have the thermal expansion, and we have the yield strength. So we should determine the weighting factor for what? For these properties and the aid of a digital logic table, and select the best material from it. So in this case, what we are supposed to do is that we are constructing the logic table, and then we are supposed to find the weighting factors. So we use the logic table to find the weighting factors, and after we need to also find the performance index, and we need to find the summation, the one which has the highest performance index. That means that that material will be used. So we have aluminum, we have the stainless steel, we have titanium, we have Inconel. So these are the properties. So we have toughness, yield strength, Young modulus, specific gravity, and thermal expansion. Okay, so with this table will help you find the scaling factor, and we use the logic table to find the weighting factor. So let's take your calculators and let's do something. So with the logic table, this is how we do it. So we have our logic table. Now one may ask, how do we even construct this table? So from what we did, we find the number of combination, and the number of combination is 10 because the number of properties is 1, 2, 3, 4, 5. It's 5, so we get 10. Now look at this arrangement. This arrangement is done per your preference. You have the material or the material property which is more important to you. Arrange it in that order. Okay, so now let's do the logic table. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, and it is 10, right? This is for total, right? We'll do some total. So we'll do the total here. And this one, let's mind this. So we have like 10 tables plus the total, and which will make us know that the combination gave us 10. So now how do we compare? Now we say that we are going to take the two properties at a time. So first we are going to take that this is my first property, this is 1, and this is 2, this is 3, this is 4, and this is 5. So I've arranged it in this way. So first for here, we're going to take toughness and strength. So we are going to take 1 and 2, right? And we are going to take toughness and density. We are going to take 1 and 3. We are going to take toughness and thermal expansion. So we are going to take 1 and 4 and compare. We are going to take toughness and stiffness, 1 and 5 and compare. Now after taking that, we are exhausted. Now we go to second. So we're going to take the strength and compare it with what? Density, 1 and 2 and 3. Then we take the strength again and compare it with what? The thermal expansion, 2 and 4. And we're going to take the strength again and compare it to what? The stiffness, so 2 and 5. And then we go to the third one, which is density. So we're going to take the density and compare with what? Thermal expansion. And we're going to take density again, 3, and compare it with what? The stiffness. And then we are going to take what? The thermal expansion, which is 4, and compare it with what? The stiffness. So we have this. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, because the number of combination was 10. And you can do that very. If it's 2, you know how to get it. Just take the first one, compare it to the 2. You take this and compare it to this. You're going to get that value, so that you do that. So now after comparing to the value, what you need to do is you are going to compare 1 and 2. So you're going to compare the toughness and the strength. Which one is more important to you? So from here, for me, for the cryogenic tank vessel, I'll think that it should be tough, right? So when I compare, toughness should be the key here. So when I compare toughness to strength, I'm going to give toughness 1 because toughness is what I want is 1, and strength is 0 because strength is not what I want. I'm going to compare toughness to density. So toughness to density, I'll take toughness to be 1 because it's more important than density for this application. So density becomes 0. Then I'll take toughness and thermal expansion. So toughness, I want it to be this one. Thermal expansion will be 0. And I'll take toughness and stiffness. I want toughness and stiffness to become. I hope you understood what I did here. It's very simple. Then we go to this one. I'm going to compare strength and what? Strength and density, right? So with strength and density, for here, strength, I'll give strength 1 and density to be 0 because I want more strength and I'm not concentrating on the density. Then we go to what? Strength and thermal expansion. So strength and thermal expansion, I want thermal expansion, so strength becomes what? 0. Then we go to what? Strength and stiffness. So I want the material, I prefer stiffness, so stiffness is what I want. So stiffness and strength become what? 0. Now then we are going to compare 3 and 4. We're going to compare density and thermal expansion, right? So then density, I want density, so density to be this and thermal expansion to be 0. And I'm going to compare density to stiffness. So with densities to stiffness, that's a 3 and 5. Density, I want density to still hold and stiffness to be what? 0. And then the last one I'm going to compare is I'm going to compare thermal expansion and stiffness. So for thermal expansion and stiffness, I will take thermal expansion and stiffness is 0. So this is the logic table I've constructed. It's very simple as that. You can do it in your own way, and I think it's your own preference, but at the end you should make it so logic. That's why it says logic. So for us to do, after that, we are going to find the total, right? So this is going to give you the total. So here we had it to be what? 4. We had here to be 1. We had here to be 2. We had here to be 2, and we had here to be 1. So after constructing this table, then you move on to the next table I'm going to go on with. So with the next table, we are going to have this one. So we have the material property, we have the positive decision, and we have the weight index or the weight, the weighting factor. So here we know that toughness, we had toughness to be what? In this case, toughness was 4, right? Yeah, you look for the table. And then we have strength. Strength was what? 1. And then we have density, that's specific density, specific gravity to be 2. We have thermal expansion to be 2, and stiffness to be what? 1. So after you add all this, and the total will give you 10. And how do we find the weighting factor or the weighting index? So how do you find the weighting factor? What you do now is that you're going to divide all this by the total. So you're going to take 4 and divide it by the total. So in this case, here, you're going to give you 0.4. Here is going to give you 0.1. Here is going to give you 0.2. Here is going to give you 0.2. Is going to give you 0.1, and the total is 1. I told you that for the weighting factor or the weighting index, it should be less than or equal to 1. So if you do it and it's more than 1, it means that your calculation is very wrong. So this is what we want. This is what we want. So now we are done finding the what. This is the weighting what? The weighting factor. The weighting factor. So we are done finding the weighting factors. But they ask us to, after finding the weighting factors, we should also what? Determine the best material. So for us to determine the best material, we need to find the scaling factor. So we are moving on to the scaling factor. And I hope you are with me. So let's go to the scaling factor. Wait. So finding the scaling factor, right? So now when we talk about the scaling factor is just the value of property divided by the maximum value times 100. Sometimes you can decide to do it in a fraction form. Someone can also decide to do it in a fraction, the percentage form. Now we have 2 formulas for it. So we have that for you to minimize the properties given to you. If you are supposed to minimize the properties, then you're going to get the numerical value of the property divided by the maximum value in the list times 100. And if you are supposed to minimize the value, you're going to take what? The lowest value in the list divided by the numerical value of the property times 100. Now what I'll advise you is that this is, if you can choose any of this formula and work with it. For this, maybe you want to density, corrosion, and they need to be minimized. But my advice here is that you can use one of the formula and you'll be consistent throughout. For example, if you're multiplying this by 100 and you are doing it in percentage form, you're doing it throughout. So what I'm saying is that with this formula, I'm going with this formula. Whether you're minimizing or maximizing, okay, if you go with this formula, at the end, you're going to get the same answer, right? So in this case, what this one means is that, right, you are going to take the numerical value. So for example, if you are working, we'll do it in the table form. You are finding the scaling factor for toughness. You are going to take the numerical value for toughness. Now we are aluminium. Toughness is 75.5 divided by the maximum value in the list, which is the total. Now note this. Sometimes in the table given to you, if they don't give you the total, you need to take the maximum value. So for instance, if this total was not given to us, the maximum value will be what? 770. So you're going to take 75.5 divided by what? 770 times 100. But in a table that the total is given to you, then you are required to use the total. Now you must use consistency. If you are using the total throughout, you must divide every calculation you do, you must divide it by the total. But if you are using the maximum value in the list, which is 770, for every calculation you do for any of the properties, you must use the total or the maximum value in the list, which is not, you are not going to combine, you are not going to use the total value. Okay, so in simple terms, if the total is not given to you, just use the maximum value in the list. If the total is given to you, use the total. So let's get into it. So with that, you need to draw a table, and this is my table for it. So my table, I've done some of the calculations to make this video very short, but I'm going to explain it. So now what I'm going to solve is for aluminum, right? So I left a space for aluminum. For the rest, you can try it because this is my work that I've done so that you can know it. But I want you to understand how I did it. So for aluminum, right? For me to find the scaling factor of aluminum, I'm going to take what? So 75.5 divided by what? 1263.5 times 100. So that's what we do. So we are going to take the value, which is 75.5, divided by what? The total times 100. And what are you going to get? Well, you are going to get 5.97. So in the second one too, for yield strength, this is yield strength, right? So you're going to get for aluminum 420 divided by the total 3850 times 100. And in that case, when you do that, you're going to get what? This to be what? 10.91. The same thing for the stiffness of the Young module. You're going to take aluminum to be what? 74.2 divided by what? The total is what? 592.2 times what? 100. And in that case, you're going to get it to be this one is going to give you 12.53. And you do it for the specific gravity, which is 2.8 divided by 23.64. And when you do that, you're going to get 11.89. And for the thermal expansion, you're going to get 21.4 divided by 5, 59.2. And you're going to get 36.5. This is how we do it. So how did I get these tables? They are all the same thing. So you go to stainless steel. Stainless steel is 770 divided by the total times 100. You're going to get this. You go to the yield strength. So 875 divided by what? 3,850 times 100. You get it. So that's what we did from here. So from getting this, this is what? The B value, which is the what? The scaling factor. So for you to do now, after getting the scaling factor, the next thing to do is that you're going to multiply the scaling factor by the weighting factor that we found. So let's get into another table, how to find the scaling factor. So for the performance index, right? So as far as we have the weighting factor, which is from the logic table, for the performance index, we have it to be, we are going to multiply the scaling factor, which is B times the W. And in this, when you sum all of them, the total performance, which you from the material which has the highest performance, that will be the material for the what property. So in this case, there we established from the logic table that we had the weighting factor. These are the weighting factor for each of what the properties. So the weighting factor for toughness is what? 0.4. So from the table, from the scaling factor that we found, which is beta, you're just going to multiply all the toughness that is there by what? 0.4. So for example, we have aluminum to be 5.97, and if you multiply 0.4 by 5.97, you're going to get 2.39. okay, that is it. And then you go to 0.1. So in that case, you go to stainless steel, you multiply the D value that you've gotten from the table that we did by 0.4, and you do that for the titanium, and you do that from the Inconel, right? And you have your table. You go to the yield strength, the same thing. The yield strength, the weighting factor was 0.1. So then you take aluminum was 10.91. So when you multiply by 0. You're going to get 1.09, right? And that's it. And then the Young modulus is the same thing. We had 12.53. When you multiply it by 0.1, you're going to get 1.25. And the specific gravity, we had it to be 11.89. And when you multiply it by 0.2, you're going to get 2.378. And for the thermal expansion, we had it to 36.15. When you multiply by 0.2, you're going to get what? 7.23. So when you are done with this, so let me take it's okay, 7.23. So when you're done with it, what you are supposed to do is that you're going to find the total of this. So you find the total here and write it here. You find the total and write it. So the total for aluminum, this plus this plus this plus this plus this. What are you going to get? When you do that, you're going to get 14.3. So 14.3 will be the total, right? Now, you also add for the same thing. What I did was for you to understand how we get this table. So you can do the same thing from stainless steel. We had this same thing. And then when you are done, the total, the one which has the highest value, will rank first. And that material will be used for the engineering application. That is the cryogenic vessel, right? So you can see that aluminum is 14.3, stainless steel is 43.52, titanium is 16.76, Inconel is 25.4. So the ranking, the highest value becomes 1. So this is 1. Then we come to 2, we come to 3, and we come to 4. So you know that from here, even though they gave us some list of material that can be used for the work, at the end we know that what the stainless steel, so the material, best material is what, the SS301. The stainless steel is a one for the application. So this is how we can find the performance index and use to select the appropriate material in material selection. And also this is the easiest way to use the logic system to find. Thank you very much for watching this video, and please kindly subscribe for more videos.